Okay, so today we're going to talk about the intermediate value theorem. And this is one of these topics that mainly has theoretical uses and is oftentimes useful in doing proofs in an analysis class. But it's an important thing that is oftentimes taught in Calc 1 as more or less an introduction to maybe the formalizations of mathematics. So really, this is going to state something that, at least on the surface, it appears to be very obvious. Okay, it states that a continuous function, when it's defined on a closed interval, is going to take every point between its endpoints. And when we say every point, we're talking about the y values of a function. So let me look at an example so that you understand what's going on. So we have this function here. It's defined on the interval from -1 to 1. And what the intermediate value says is if you look at the y values, which coincidentally also land from -1 to 1, although they don't have to be the case, you'll notice that this function is going to take every value on that interval. So notice that no matter what the value is, it's going to take that. And it kind of makes sense when you think about what a continuous function is. Remember, we defined it as kind of a function that you can draw without lifting your pencil. So it obviously makes sense that if I draw any function that's continuous from -1 to 1 and it has these endpoints, so I can draw another function, so I can do something like this. As long as it's continuous, and it is a function, so it passes the vertical line test, it will basically take on every value between the two horizontal blue lines here. Okay. Now, the reason why this is important to state, even though it seems obvious, is because it's actually a little bit difficult to prove and beyond the scope of a Calc 1 class when trying to deal with this. And that's because this idea of defining a continuous function based on drawing it without lifting your pencil is kind of informal. There's a more rigorous way to state what a continuous function is, and it's not just based on the graph, but it's based on some other things. So that's why we oftentimes... Well, this is actually a non-trivial type of statement. Formally, the way that this is written is that it says that if f of x is continuous on some interval from a to b, so these are the x values that we're talking about. So if I was going to draw a function, and we have a and we have b here, and we have f of a and f of b, again, one doesn't necessarily have to be bigger than the other, so f of a might be here, and f of b, for all we know, might be down here. Then for every value m between the two, so if f of b is down here, and you imagine that we've got this y interval here, and we're looking at every value m that lies somewhere on that curve. Remember, that's what this upside down a means. It means for all. Then there exists, so this backwards e means there exists. So a lot of mathematical shorthand. A c value in here, such that f of c equals to m. So again, if I try to draw a continuous function here, although that's probably not a good example, we don't want a function to double back on itself, but if I draw a continuous function here, and let's say I choose a particular m here, so now we're choosing an individual m, then there has to be some value c between the two, where f of c is equal to m. Okay, so how is this actually practically useful? Again, it's mostly useful for proofs, and it's mostly useful for proofs in classes that are well beyond Calc 1 when you want to deal with the formal mathematical issues at hand. But we can do a couple things. So one thing we can do with the intermediate value theorem is we can prove that sine of x equals 0.3, we can prove that that has a solution. So that means that there is going to be some value of x such that sine of whatever that value is equal to 0.3. And we're going to use the intermediate value theorem. So how do we do this? Well, first, we know that sine of x, and again, we haven't proven this, but we've at least stated it, that sine of x is continuous everywhere. And because the intermediate value theorem requires an interval, we're going to just deal with the interval from 0 to pi over 2. So if you remember what sine looks like from 0 to pi over 2, we have 0 here, we'll have pi over 2 here, and it's going to be 1 up there. So it's going to look something like that, the part of the curve. We know that sine of 0 is equal to 0, and we know that sine of pi over 2 is equal to 1. And thus, the intermediate value theorem will state that for every value of m between the two, so that's every y value m somewhere on this interval, there's going to exist some c in here such that f of that the sign of that function, the value of the function, is equal to m. So, well, in our particular example, 0.3 is such an m, so it says it holds true for every m, so that means m equals 0.3 works because 0.3 is in the interval from 0 to 1, so we'll just select a particular interval here. We'll say 0.3, and again, there's going to exist some c value. Probably need to move it over a little bit, but some c value such that the sine of c is equal to 0.3. One thing you'll notice here is that we haven't actually found the c value here, which is really an interesting thing in mathematics because something that's very common is this notion that we can show that something exists without actually finding it. So we know that c exists. We know there's some value, and you could take the inverse sine of 0.3 and find that. That's fine, but the key here is that we're actually proving that this has a solution without actually finding the solution, which if you haven't seen that before in math, it's a bit of a strange thing, but there are many instances where we can prove that something exists without actually determining where it is or what it is. So this is the intermediate value theorem. And again, I hope that this video was helpful, and as always, take care.